I'm gonna open up an Excel file that we have, and let me see if I can't find it here. We have an Excel file online called Descriptive Statistics Example. Okay, and I'm actually going to work with a real sample. Okay, so here's my real sample. Right, it's a sample of size 30. It's not a tremendous sample. It's not a small sample, but it's not a big sample either. Sample size. The statisticians start to treat samples differently once they start to get over 30 or 40 or 50. If they're smaller than 30, they have to be really careful with them, and we're going to get into that as we proceed next week. Okay, so now let's see what I have here. I got a sample of size 30. Okay, whatever these happen to be, sample size 30. I have that already. I'm going to find the mean of this sample. Okay, if you guys open it up, you're going to be able to do the same thing I do. I'm just going to find the average, and I'm going to highlight the whole thing. Okay, the average is 69.8. I'm going to find the standard deviation. Okay, I'm going to enter. Okay, now that standard deviation, is it the standard deviation of the population or is it the standard deviation of the sample? Sample, right? So we would indicate SD, right? So now really, I can't use my formula. I need the population standard deviation, right? But I don't know it. Since I don't know it, I have to work with what I have. This is all that I have. The mean, since this is a random sample, the mean approximates the mean of the population. Mean of the sample approximates the mean of the population. Similarly, since we're picking people at random out of the population, the distribution of these numbers mimics the distribution of the population. So the standard deviation of the sample also approximates the standard deviation of the population. Is it as accurate as the population? If I knew the population standard deviation, no. Next week, we're going to make some adjustments for that. In fact, the next step here, you're going to see we're not going to do it, but the software is going to do it. So right now, we're going to work with what we got. So if I assume that the standard deviation is 3 point, and I'm sorry, I know I turned away. I hope you guys could hear some of that. Okay. If I want to approximate the standard error is going to be equal to my standard deviation divided by the square root of my sample size. And my sample size was 30. Okay, so that's my standard error is 0.64. Now, I'm going to apply that formula that we were working with before to find the lower bound, the lower number in our confidence interval. Okay, what's that going to be equal to? It's going to be equal to the mean, which is 69.8, minus what number if I'm doing a 95% confidence interval? Maria, what would I use if I'm doing a 99? 2.58, right? And if I'm doing a 90, 1.64, right? These numbers are going to become second nature. You're going to remember them like they're your anniversary, right? Not that well, hopefully better. Yeah, so 1.96. We're going to do a 95% confidence. So not 1.96 times 96 times the standard error, okay, 0.64. Okay, I'm going to hit enter. And my lower bound for my confidence interval is 68.54. My upper bound is equal to, what's it equal to? It's equal to the mean, except this time I'm adding 1.96 times the standard error times the standard error. Okay, now before I hit enter, one of the reasons why the 99% confidence interval is wider than the 95 and the 90 is what number am I using for the 95% confidence interval? 1.96. If I were calculating the 99% confidence interval, I would be using 2.58. So you would in effect be adding and subtracting a bigger number from the mean. So it makes your confidence interval wider. That ties right into the idea of why you look at it, why a confidence interval that's higher, it has to be wider, right? The formula mimics your understanding, follows your understanding of why the confidence interval has to be wider. If we're willing to be only 90% certain, right, we would only use 1.64. So 1.64 times the same standard error is going to be a smaller number you subtract or add on both sides. So the range is going to be smaller. Okay, so all this stuff kind of ties in together. I'm going to hit enter and find out what it is, 68.54 and 71.05. Okay, that's our confidence interval. Yeah, I see a couple of hands. Oh, okay, I'm sorry. I could have done it separately. Equals square root. That's a function that's built into Excel. Okay, parentheses. Notice that as soon as I put the parentheses in, it's waiting for me to put a number in there. I could either put in the number 30 and close the parentheses and hit enter, or I could also equal square root, parentheses, and just click on the cell that has 30 in it, and it'll do the same thing. Okay, everybody comfortable with that? Now, now you could also, if you don't know the functions, you can click on here, and it'll bring up a search box where you can actually look up the function and get some help with it and so on and so forth. When I did it over here, I combined the two actions. Equals, oops, put in equals, oops, I got to get rid of this. So it knows I'm not doing that anymore. Equals, okay, the mean plus, actually minus for this row, minus 1.96 times, asterisk means times, square root of, I could type in 30 or I could click in this box, means the same thing, right? Now notice I didn't have to put in any more parentheses because I know that Excel is going to first resolve it from the higher power operation to the lower. So if there's if there are any exponentials in here, it'll resolve them first. If there's a multiply or divide, it'll resolve them next. If there's an add or subtract, it'll do them last. So in other words, if I really wanted to be careful, I'd put a parentheses around here and over here, just to make sure it did that first. Took 1.96, multiplied it by that before subtracting it from the mean, right? So that I come up with a, whoops, what did I just do there? 1.96 the square root, d6, did I hit click, did I check the right mean? 1.96 times the square root. Oh, the standard error, I'm sorry, I chose the, okay. Oh, I'm sorry. I didn't pick this. I put in the sample size instead of the standard error. Oh, no. I forgot. I know what I did. I'm going to leave 30 in there, and I forgot to put in 1.96 times standard error, which is 0.64 divided by the square root of 30. Right? So still, it's going to work out the division and the multiplication before it does the subtraction. So it's not going to mess up the result. I did it again. What am I doing wrong though? Yeah, is that what it is? Equals, I'm going to try one last time. Mean minus, right, 1.96 times standard error. Oh, excuse me, just the standard error. Period. Done. Right. I didn't need the square root of that. I had already used it to calculate the standard error. Everybody see that? Did I confuse you too much? Right. In other words, 1.96, right, times the standard error. I don't have to use it's X bar plus or minus 1.96 times the standard error. Or in other words, the mean minus, first I'm going to do minus 1.96 times the standard error, which is 0.064. Okay, I don't need the parentheses again because it'll do the multiplication before it does the subtraction. Okay, so you guys could replicate this if you needed to, right? And you're gonna on the homework. I'm gonna show you a brief look at the homework when we move on a little bit. Now, just to show you, 68.54, 71.05. I'm gonna put this aside for now, and I'm gonna open up an SPSS file with the same numbers. Okay, it's on Blackboard if you want to open it yourself. I'm gonna double click it, get SPSS to open it. It's gonna take you a little bit longer because I already had SPSS open. I don't want to get to that. Okay, so now these are all the same numbers that we had before. There's 30 of them, just like before. I didn't bother to give it a variable name or anything like that. And I'm going to calculate the mean and the standard error for this sample and also the confidence interval. I'm going to click on Analyze. And mean, standard deviation, standard error, those are all descriptive statistics. Unfortunately, I have a number of choices here. The first three choices all have some sort of function associated strictly with descriptive statistics. Frequencies just doesn't count. Just counts how many males, how many females, mostly more applicable to categorical or nominal data than anything else. Because you're not going to want to count, if you count every exact value for like blood lead level, it's going to be kind of messy. If you look at you could have a sample of 30 children and not two of them might have exactly the same number, right? Even though you can find the mean of it and predict what the distribution is. So frequencies doesn't work too well with numerical data. It's usually for categorical data. So if I go down to descriptives, I can do descriptives here. I'm going to move this into the box, which lets SPSS know which variable I want to work with. Options probably says, oh, let's do the variance, standard error, and so on and so forth. Oh, you can do standard error here. Okay, let's see if it does it for us. And say, okay, see what we get. Okay, here we go. We got the mean, okay, which is 69.80, same thing we got before. The standard error, which is 0.642, which I think is the same as what we got before. Standard deviation, 3.517, same as we got before, so on and so forth. They also calculated the variance, which is just the square of the standard deviation, or the vice versa. The standard deviation is the square root of the variance. We had done that earlier. Okay, so now the problem here is we don't have a confidence interval. We could use these numbers to calculate it, right? We got the mean and we got the standard error. So if we want 95% confidence interval, we just take this number, 69.8, and subtract 1.96 times 0.642, or add 1.96 times 0.642, and that'll give us those values. The thing is, though, is instead of using that function, I'm going to go back to Analyze. I'm going to go one step further, which is Explore. Explore does the same kind of stuff, but it gives me a little bit more flexibility in terms of how I handle the data, analyze the data, and what information it gives back to me. I'm going to move my variable of interest into my dependence list. If there were more than one, I could move more than one and do all the same operations on each one of them. Now, if I had, for instance, said that some of these are males and some of these are females, I could take gender and move it into this factor list, and it would find means and standard deviations separately for females and males. I don't have that situation right now. I'm going to click on statistics. Right. The interesting thing is that you only got one choice here. Either you're going to find descriptives or you're not going to find descriptives. So you want to have that checked off. Now, the confidence interval for the mean, conveniently, it lets you decide what you want. 90, 95, 99. You could even, if you want, put 89.5 in there. It'll calculate any confidence interval that you want. Okay, remember, the way it decides what number to add, multiply by the standard error by is what the confidence interval that you want, what percentage of certainty that you want, that you capture the mean within that range. So you literally could define 73.3 confidence interval of 73.3% if you wanted to, right? You would just have to go to the Z table and look up what Z-score that would represent. Okay, so I'm going to stick with 95% because I'm sane. And then let's see, plots. I could do plots if I wanted to. It's automatically going to do box plots for me. I don't think I need histograms. I'm going to click OK. Okay, it's going to do the same basic calculations for me, but it's going to give me a bit more information. Here we go. So the mean is 69.8, same as before. The median, this variance, the standard deviation. So Explorer is going to be a go-to for us. Analyze, descriptive statistics. Explorer is kind of our go-to spot for all of these descriptive statistics we might want. So the standard deviation is 3.14. It also calculates for us, where is it? The standard error should be here somewhere, I think. Did it calculate it for us? Is it? Oh, there it is on right there, right? That's the same one we calculated. Okay, so now it goes ahead and uses those two and actually calculates our 95% confidence interval. Remember, we actually typed that into that box. The lower bound is 68.49, and the upper bound is 71.11. What did I get before? Let me move this out of the way. Let me get my Excel spreadsheet up. Okay, here we go. And what did I get before? Let me move this. Let's see. This says 69, excuse me. This says 68.49. I got 68.54. It's different, right? That one is wider. It's further away from the mean, and 71.11 and 71.05. Why would SPSS make that interval wider than I did when I did it in Excel? What could it be making up? Remember, you make it wider, you're making up for error. You're assuming that there's going to be more error than I anticipated. What's introducing the error that made SPSS make that a wider interval? The chance, yeah, kind of chance. Of course, chance is always what this is all about, right? What did I tell you about the standard deviation we used? Was it population standard deviation? No, it was the sample standard deviation. SPSS is adjusting for the fact that I didn't know the population standard deviation and making the interval a little bit wider than just 1.96. Okay, now that's very interesting that it does that. What do you think would affect how much wider it makes it? What would make our standard deviation of the sample a more accurate approximation of the population standard deviation? Larger, and a larger sample size would give us more confidence. Basically, once we get above 30 or 40 or 50, we don't worry about the fact that we don't know the population standard deviation. We make believe we do. Okay? SPSS is a machine. It doesn't care. It always calculates the exact number. If the sample size were 1,000, it would be a little bit different than 1.96 times the standard error anyway. It'd still be a little bit, teeny bit wider. Right? So that's what it's doing there. So you guys could probably use this to check your answers if we have, if you have the data to start off with. Okay, I'm going to open up the homework. When we get to the exam, we're going to give you rules for that. We're going to tell you if the sample size is bigger than 30 or larger, you handle it this way. If the sample size is smaller than 30, you handle it this other way, right? But you want to know something? You guys are actually, believe it or not, getting ahead of us, right? So that must mean you're catching on, right? No, that's exactly what it means. You thought ahead. Yes. Exactly right. And what would make the answer so close, very closer? The bigger the sample size, right? So what I'm telling you is if the sample size is bigger than 30, the answers are going to be close enough for you not have to worry about the difference. Just take whatever you got in Excel, right? Yeah. What we're gonna be getting to that next week. Literally getting to exactly that point next week. And basically, what we're saying is that once the sample size is bigger than 30, right, you can use the less conservative version. In other words, you can say that the range is smaller than you would have said if it were smaller than 30. Don't worry about that now. You're getting way ahead of us here. Okay? But the main thing you want to do this week is to be able to calculate these values. I'm going to show you one more version of this, okay, which is a little bit of a twist. And I'm not sure if you covered this already, but it's going to come up. Okay, and I'm going to go over here to exercise number 4. Suppose we're going to apply this same rule to a proportion. Okay, before I go in any further with proportions, okay, when I'm working with proportions, I'm working with the same kind of thing. So for instance, if I were to say to you that, let's see, P, okay, or actually rho is equal to 0.30. 30% of this population has a driver's license, right? Okay, 0.30 is my percentage of the population that has a driver's license, this particular population. Okay, so now let's say I were to tell you, I'm going to take a sample equal to 100 from another population. And I find that out of that population, 35 people have driver's license. What is the average that I have there? I'm going to call that P cap. Why am I calling it P cap instead of P? Because this is a proportion of a sample where I was talking about the proportion of the entire population. So P cap is a sample proportion. 35 people out of 100 have a driver's license, so the proportion of people is equal to what? 0.35. Everybody agree with me there, right? So now let's say I took many samples of size 100. Okay, sometimes if the population has about that proportion, a lot of the time, half of the time, I will take a sample of 100 people, and sometimes they're going to be above 0.35, sometimes they're going to be below 0.35, because that's the way samples are. It's less likely that I'm going to be far away from 0.35 or far away from, or much lower than 0.35. Same reason that we don't expect to get really unusual results when we take a sample of any other kind of numerical variable. Okay, so now I need a way to estimate how spread out this distribution of all these samples is, right? So I need a standard error for this, just like I need a standard error for a numerical variable. Anybody remember how you calculate standard error for a proportion? It's the square root of, give me a guess, P times 1 minus P, right? Seems like that comes up a lot, over N, sample size. Again, bigger the sample size, the smaller this number becomes, just like before. Okay, so what is this number? What is this standard error equal to? It's equal to the square root of 0.35, and what's 1 minus P? Times, what is that? It's 0.35, 1 minus 0.35 is 0.65, right? Divided by 100. So what is this equal to? Let's calculate it. Okay, I'm going to get to you guys, Danielle. I'll get to you guys in a sec. Okay, hang on a second. Okay, so let's see. 0.35 times 0.65 divided by 100 equals 0.002. Is that my standard error? Is that the answer? What have I forgotten to do? Got to find square root of it. So my standard error is 0.04. I'm going to round it off to 8. 0.048. My standard error is equal to 0.048. So now if I want a 95% confidence interval for the true population that I'm comparing this other known population to, where my sample came out to be 0.035, well, what do you think I would do to find my confidence interval? What did I do before? I started with the mean and I added or subtracted 1.96 times the standard error. Well, why would this be any different? Let's start with the mean. In this case, the mean is a proportion. Let's start with P cap plus or minus 1.96, because what confidence interval is this? 95%, times the standard error, which is 0.048. Okay, so what's my confidence interval? My confidence interval is, let me get my calculator back. My confidence interval is a 0.3, oh, bless you, 1.96, 0.96 times 0.048. That's that number. I did that first because I'm going to store that into my memory so I can clear this. And I'm going to take 0.35 minus that value I stored into memory, which was 1.96 times the standard error. And that's equal to 25.6. or 0.256. Okay, what about the upper end? Well, the upper end, I'm going to be adding it instead, right? So I'm going to go back and I'm going to say, let's see, clear this value. And it's going to be 0.35 minus that value. Whoops, I made a mistake there. I should have said plus. 0.35 plus this value is going to be 44.4. Or I could 0.44. 44.4 was it? 0.444. Okay, so 0.2, I'm 95% certain that the true population proportion for this population, where I got a proportion of 35% of the people had driver's licenses, is between 25 and 44% of the people have driver's licenses. Can I say that it's different from this other population I know? I can't. Because this population could very well be 30%. It's within my confidence range, right? If I had another population, say California, where a lot of people have driver's licenses, and the population proportion for California is 49%, right? Can I say that I'm 95% sure my population is different than California? Can I say it's different there? I can. Because, why can I say it? Because I'm 95% sure that it's from 25 to 44%. So if I'm comparing to a population I know is 49, I know I'm 95% sure it's different than 49, right? Because I know it should be between these two numbers. Does that make sense to you guys? That's kind of a challenging thing, right? But it's the basis for a lot of stuff we're going to be doing in the future. Let me see faces here. Like these brave eyes. Makes sense, right? Not really that hard, right? Let me go back here. Okay, let's see what I got here. Use the settings are going to be in. Yeah, I want to get these questions on here. Another question. I don't question. Oh, I'm sorry. That's right. You guys can't hear the question when you're online. I'll make sure of that. Should we be using 3.3 since the formula asks for a P, not P cap? Well, remember that I'm actually looking at a population that I don't know the mean of. Hey guys, the question was, should I be using 0.3 for the mean instead of 0.35? Right? Well, this is the percentage of people in a different population. I'm sorry, but I don't remember exactly what the problem I wrote asked. I kind of changed the problem a little bit on, as I was working, because I wanted to include this conversation about, when we can say that we're sure there's a difference between one population and another. So in this case, the way I described it here, this is the known population proportion, like the population mean or population proportion for one group. And then I took a sample of another group and found that 3,500 or 35% of those people. So the only thing I know about this population, right, is that my mean of my sample is 35%. So that's the only thing I can use to calculate my confidence interval. Okay, and that's going to be the case 99%. I hate to use numbers like that because we're throwing them around like it's crazy, right? I'm almost always going to be using this. It's almost always going to be this situation because the whole point of this is we don't know the true population proportion or the true population mean. We're using this as a way to estimate what it is, and along with a range that we can have a certain level of confidence that the true population mean will be captured by that range, will be included in that range. Let me back up here. I'm not sure about this question about the 49%. Where did 49%? Oh, 49%. Yeah, 49% is the percentage of people in a different population. In other words, that's the population proportion for people in California. These are people in, say, Brooklyn, right? That's the known population proportion in California. Now, I don't know the population proportion for Brooklyn. All I know is the sample 100 people that I had was equal to 0.35 or 35% had driver's licenses. when I calculated my confidence interval, it told me that I'm 95% confident that between 25% and 44% of people in Brooklyn have driver's licenses, right? So I'm 95% sure that it's less than 49%. So I can say I'm 95% sure that they're different. If the population proportion for California had been 43%, well, I don't know if the true population proportion for Brooklyn is 25 or 44. So I can't say that it's different with 95% certainty from 43. But I could say it's different with 95% certainty from 49 because it's outside of my range that I have 95% confidence that it's in. Okay? Does that help a little bit? Okay, you're going to get plenty of practice in this. I'm about to open up the homework. Okay, the homework assignment looks something like this. And you're going to get a number of these problems there. Now, there's a homework's not, the next homework, Levi, the next homework is not going to be presented except for 2 weeks. So we're going to do this for, is this going to be 1 week? Should we give them 1 week or 2 weeks to do this homework? Know what I'm saying? In other words, you know, unless we want to get them the next homework early. Why don't we figure 10 days? We give you 10 days on this at least, right? Because there's a lot of problems here. Give you a chance to play around with it a bit. A week and a half. I'll post the date. We might get the next homework up, but you got at least 10 days to do it. Okay, you got at least 10 days, maybe a little bit longer. Hopefully, I'm hoping we can get the next homework up a little early, so that way, because like you're gonna have a shorter week. If it's only a week, there's a test at the end of that week, so you're gonna have to get it in by Friday or something like that. Maybe we'll buy you some time on the other end for that homework by making this one due a little bit earlier. Okay. I'm sorry. Yes, you guys. The question was, you're going to get multiple tries to complete the homework, and the answer to that is yes. I'm only going to count the last version that you submit. Okay, so here it is. I gave you an individual page for each one of them so you can show your work. Whoop, I got the wrong thing. The lab exercise. Let's save. Example, here we go. Here we go. Okay, so you can see that this is going to ask you a number of different questions about populations and samples. Okay, and the first thing you're always going to do is you're going to read the problem carefully, and you're going to make a decision. Am I dealing with a population or am I dealing with a sample? That's the first thing you need to look at, right? Because that will tell you whether or not you're working with a population mean and standard deviation, or if you're working with a sample mean and standard deviation, and if you're going to be dealing with a standard error, and so on and so forth. So you have a number of these. Okay, I left a space for you to work below that area, and then to put your answers in here so I can go through them easily and grade them quickly. But if there's something wrong here, let's say you get C wrong, it'll give me an opportunity to take a look at your work and either give you some feedback on it or perhaps even give you part credit. So I left you plenty of space between each problem so that you could enter your answers, just a number that we're asking for, the answer there, and then leave your work down below it. You can add extra pages to this if you want to. So you're going to download this as a Word document. Instead of completing it online like the test versions, you'll have this on your computer, your Word document. You'll be able to work with it directly and so on and so forth, and then upload it to the assignments tab. Okay, you'll see in the assignments, you'll see assignment number 3, and you'll see that you can upload a file and so on and so forth. And it will let you upload multiple versions of it. It won't shut you out. You can just, after you do it once, if you see some errors, you can go back and do it a second time. And like I said, I'm only going to grade the last version that you put up there. Okay, if you're having problems with a particular problem, it's going to be insane if you guys all ask me, "Oh, Tony, I'll go over my homework, before it's finally due," and I get 50 people doing to that, I like have to quit my day job. So if you have a particular problem that's an issue, email me, and maybe between now and the time that it's due, I can do maybe half hour, an hour online, so we can go over problems that are similar to the ones that are giving you issues. Okay, and there are, I believe, there's 8 problems I put up. So there's 8 problems. So don't ask me to do all 8 problems. Ask me to do number 2 and number 3 are hard. They're different. How do I handle them? Okay. So and if you give me some feedback, I'll know which ones to work with when we do it online. Okay. No, statistics is not my day job. Thank you very much. Okay. So at any rate, we're about 8:37. At this point, why don't you guys get started on the homework or the 1 or 2 problems that I skipped over in the exercise? And why don't you go ahead and start working on the homework? And I'm going to circulate. You're going to have an advantage of those people that were just too lazy to come into class tonight. So if you need me to, I'll look over your shoulder and I'll maybe help you out on some of the problems. So maybe you want to, if you have time, you want to stick around. Stick around for the next, we're done in 10 minutes anyway, but if you want to stick around till 9, like about 20 minutes or so, stick around and I'll look over your shoulder and you get a chance to start on it and see if it makes sense to you. Okay, you guys online? I'm going to leave the computer open online. That's not fair. I'm going to leave the computer. I'll make it fair. I'm going to leave the computer online open as well. So if you guys start working on the first couple of problems or the third problem, give it a shot. And if you have a question on it, type it in, and I'll come back every few minutes and check on what the questions are. Okay. Otherwise, if you had enough, you can hang up, and you won't be disadvantaged, I don't think.